You are about to view the first part of the notes for Chapter 4, dealing with forces and the laws of motion. What is a force? What effect do forces have? What are the units used to measure forces? Forces represent the interaction of an object with its environment. It takes a force to start an object moving, or to stop an object, or to change an object's direction of motion or its shape. Forces can act through physical contact, such as a push or a pull, or forces can act at a distance, such as gravity and electromagnetic forces are field forces, and they don't require a contact but just the interaction of the fields. Forces are vectors, so you must keep track of their direction. The unit of force is the Newton, symbolized by capital N. It was named to honor Sir Isaac Newton, who discovered the three laws of motion that explain so much about what we know about the movement of objects. And 1 Newton is defined as the force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. One of the most important tools you can use to help you solve problems in physics is to draw a picture. Such pictures are called free body diagrams. Free body diagrams show the forces acting on an object. The forces are visualized by drawing arrows to represent the forces. The length of the arrow is proportional to the size of the force, and the direction that the arrow points is the direction that the force is acting. Let me show you an example. Say we have a car that crashes into a wall. Here the free body diagrams are shown for the car and the wall. Note the free body diagram shows only the forces acting on the object, not the forces the object are exerting on any other object. So for the car, you have the force of gravity, the weight of the car, acting down. You have the force of the road, called the normal force, acting up. And you have the force of the wall pushing to the right on the car. So these are the three forces acting on the car. The wall has a force acting to the right, the force of the car bumping into the wall. You have the weight of the wall acting down, and the force of the surface pushing up on the wall, called the normal force. And these are the three forces acting on the wall. So this would be the free body diagram for the wall. This would be a free body diagram for the car. A free body diagram does not have to be an accurate sketch of the object. You can depict the object as a very rough sketch, or even a simple square or circle. The most important part is to indicate the forces acting on that object with arrows. And it's important to label the arrows with either the magnitude of the force or a name that will distinguish it from other forces acting on the object. Be sure that the length of the arrow approximates the size of the force, and the direction of the arrow points in the direction that the force is acting on the object. So for an example, a free body diagram of a flower pot falling from a windowsill, ignoring air resistance, could look like this, where the circle represents the flower pot. If we ignore air resistance, the only force then acting on the flower pot would be the force of gravity pulling down on the flower pot. A free body diagram of a skydiver falling downward with his parachute open so that he falls at a constant speed might look like this. So the circle here represents the skydiver. You have two forces acting on the skydiver. His weight, or known as the force of gravity, pulling down, and the force of the air resistance, acting up against his parachute, acting up, so the arrow points up. And if the skydiver is falling at a constant speed, that means these two forces are balanced. They're equal in size. So try to draw the arrows the same size, but pointing in opposite directions, because the gravity acts down and the air resistance acts up. Newton's first law of motion states that an object at rest will remain at rest. An object in motion will continue in the same state of motion, moving in a straight line and at a constant velocity unless a net force acts on it. A net force is an unbalanced force, or a resultant force acting on an object. In the last chapter, when we were calculating resultant displacements or resultant forces or resultant velocities, you were calculating net displacement, net forces, net velocities. Net is just another word for resultant. So when you are calculating net forces in this chapter, you will do it just like you calculated the resultant forces in the last chapter. So for an example, if you have two forces acting on this object, 5 newtons to the right, 2 newtons to the left, the net force would be 3 newtons to the right. You've got two forces acting in opposite directions. When vectors act in opposite directions, you subtract and keep the direction of the largest vector. So the net or result force felt by this object would be 3 newtons to the right. Newton's first law is sometimes stated as an object likes to keep on doing what it's already doing. If an object's at rest, it wants to stay at rest. If an object is moving, it wants to continue in the same state of motion. It wants to move in a straight line at whatever speed it's going at. The tendency of this object to remain in the same state of motion is called inertia, and this will happen as long as the forces are balanced. Balanced forces are equal in size, opposite in direction. For example, this box here. If you have two people pushing on it, each with 10 newtons of force in opposite directions, the forces cancel each other out. No net force is acting on this box, and it will remain at rest. Likewise, if you have a tug-of-war team, two teams pulling in opposite direction with the same amount of force, the rope isn't going to go anywhere because the forces are balanced. It's like they cancel each other out. So the net force is 0, and the object will remain in the same state of motion. If you're driving down the road, once you're up to a particular speed and you want to put on your cruise control, at that point, the force of friction is exactly balanced by the thrust of your engine, and at that point, you will maintain your same state of motion. You will continue to move in a straight line at a constant speed. So balanced forces are equal in size, opposite in direction, and if the balanced forces are balanced, then there is no net force acting on an object. The net force would be 0. So the object acceleration or change in velocity would be 0. Newton's first law describes objects in equilibrium, whether they are at rest or moving with a constant velocity. If an object is in equilibrium, the net force acting on it must be 0. To determine if an object is in equilibrium, calculate the resultant force acting on the object. If it's 0, then the object is in equilibrium, and that object will remain at rest if it's resting, or if it's moving, it will continue to move in a straight line at a constant speed. If the net force is not 0, then the object is not in equilibrium, and its motion will change. It will accelerate. But that's the subject of Newton's second law. Let's try a couple more example problems dealing with net forces. Let's say a lawnmower is being pushed with a 25 Newton force along the handle, which is angled at 25 degrees above the ground. What is the horizontal force acting on the lawnmower? And if friction is providing a 2 Newton force acting in the opposite direction, what is the net horizontal force acting on the lawnmower? Our free body diagram would look something like this, where the square here represents the lawnmower, the arrow here represents the 25 Newton of force acting at a 25 degree angle along the handle, and the horizontal component would be the x component, which is adjacent to the angle, and you have the hypotenuse. So to find the horizontal force, you would multiply the cosine of 25 times the hypotenuse, giving you a horizontal force of 23 newtons, which, if the lawnmower is moving to the right, the horizontal force, or the x force, would be acting toward the right. If friction provides 2 newtons of force in the opposite direction, then the net force would be the difference between the force of the handle and friction. 23 minus 2 gives you a net force of 21 newtons to the right. Finally, if there is a net force acting on an object, an additional force equal and opposite to the net force could put the object into equilibrium. For an example, if a man is pulling on his dog with a force of 15 newtons east, say a net force of 15 newtons east, an additional force of 15 newtons west would put the dog back into equilibrium. So the additional force that puts an object back into equilibrium is called the equilibrant, and it just kind of balances the forces, put the object back into equilibrium.